Welcome. Today we will be looking at vector functions and parameterized curves. Uh, let's first recall how we parameterized a given straight line. So here, let's say I have a straight line in green that passes through the point P, and that is parallel to a given vector A. So what do we mean by parameterizing the line? Well, we mean that we are looking for a function out of t which takes as input a real number t, and then its output would be a point on the straight line. So how do we do this? Well, so notice that if I look at so let's say, okay, so the green point is the given point P, 2, 1, 0, and the pink point is an arbitrary point on the line. So notice that so this arrow right here, this is the position vector of the pink point. Now the position vector of the pink point is equal to the position vector of P plus the green vector right here that goes from the green point to the pink point. So the position vector of the pink point, that is the vector from the origin to the pink point, is the same as the position vector of P, that is the vector from the origin to P, plus the green vector. But the green vector is parallel to A, so the green vector is a multiple of A. So let's say the green vector is t times A. So what we see is that if I add P to the green vector, which is t times A, that's going to give me the position vector of the pink point. So if I define the function out of t to be P plus TA, so then out of t is the position vector of the pink point, and or you can just say this is the point, and its tip is basically the pink point. So this out of t here then is what? So this is I'm adding P and TA. So P, so 2 plus 2 times t, 1 plus t, and then 0 plus 2t. So you remember we're adding P to t times A. So then out of t would be 2 plus 2t, comma 1 plus t, comma 2t. And in other words, the out of t would be a position vector, or you can say it's a point where the x coordinate is 2 plus 2t, the y coordinate of out of t is 1 plus t, and the z coordinate of out of t is 2t. So this function out of t, which is a vector valued function of a real variable t, this is a vector function, and it's called a parameterization of this straight line. So the parameterization of the straight line is basically a vector function like this. So more generally, how do we represent an arbitrary curve or a path in the n space? So for simplicity, I'm just going to draw curves in the 2 space, and my discussion here equally applies to any other curves in any other dimensions. So if I have a curve C, then what do I mean by a parameterization of the curve? Well, by the parameterization of the curve C, we mean a vector function out of t equal to x of t comma y of t, such that each point on the curve is the value of out of t at some real input t. And such a vector function is called a parameterization of C. So here I denotes the domain of this function. Now, the parameterization of a curve C is also a model of C as the path of a moving object. So, in other words, what I'm trying to say here is that I can think of R of t giving me the position vector of a moving object at time t. So you can think of C, for example, as a racetrack, and you can think of R of t as the position vector of a race car on this track. So the tip of R of t, as drawn from the origin, is a point on this on the curve. Now, a given curve has many different parameterizations, and that kind of makes sense because the same racetrack having race cars with different position, so there are many race cars on the same racetrack with different position functions, right? So a given curve or the same path may have many different parameterizations. So if I have two race cars on this racetrack, they may have different position functions, and we'll see in examples of what I'm trying to say here. So let's take an example here. Let's take R of t to be the position vector of a bug moving in the 2 space at time t. And let's say R of t is given by the following formulas. So x of t, the x coordinate of R of t is given by t, and y coordinate of R of t is t squared. That is t comma t squared. That's the position of the bug at time t. So these are the x and y coordinates of the bug at time t. Now, what is the path here? What is the path, and how is that path traced? Well, notice that to see what the path is, notice that the x coordinate of the bug and y coordinate of the bug, they have a relationship. That is clearly the y coordinate of the bug is the square of the x coordinate. So that means the bug is moving on this parabola. Now notice that we are also given that time starts at t and progresses forward. So then we can say, okay, the bug is moving on this parabola, but the question is which part of the parabola and how is it traced? How is the bug, in what manner is it traveling on this parabola? Well, notice that as t progresses from 0 to infinity, the x coordinate is also progressing from 0 to infinity, and the y coordinate is progressing from 0 to infinity. So that tells us that the bug, notice that at time 0, the bug is at the point 0, 0, right here, and then it is moving up in this direction. So that's how the curve is, the parabola is traced here. And that also tells us that the path of this this curve, this curve is not the entire parabola, right? It is only the right half of the parabola. Okay, so let's look at another example. So in this time, I'm taking R of t to be given by the following formula. So x is root of t and y is t. Again, I'm taking t to be greater than or equal to 0. Is that the same path as in example 1? Well, the answer is yes, because if you look at the relationship between the y coordinate and the x coordinate, we see that y is still the square of x. So we know that r of t is still tracing the parabola y is equal to x squared. But is it still the right half, and is it still traced the same way? Well, the answer is yes, because if you look at x, at time 0, we get the point 0, 0, and as time progresses forward, x is also increasing from 0 to infinity, y is increasing from 0 to infinity. So we still see that we get the same curve traced in the same way with this different formulas for the position function r of t. So if you think of r of t as the position of a moving bug on the parabola, then definitely the position functions are different. However, the paths are the same. That is, let's say the first example, this is the position function of bug number 1, and in the example 2, the position function is the r of t is the position function of bug number 2. So they have different position functions, but they have the same exact path. They are moving along the same path. Of course, what is different about them is, as you'll see later, is that yes, they have the same paths, but they will have, because their position functions are different, they will have different velocity and acceleration vectors. Okay, another example is I'm taking I'm taking a curve here where x is t squared, y is t to the 4, and t is less than or equal to 0. Now again, notice that y is the square of x, so we still have that this curve is this parametrization is giving us a parabola. So the curve is still a parabola, but is it the right half or the left half, or in how is it traced? Well, let's notice that as t progresses from negative infinity to 0, then x is going from infinity, x is t squared, so it's going to go from infinity to 0, and y is going to go from infinity to 0 as well. So because x is positive, that tells us in this given, for the given values of t, x coordinate is positive, so we get the right half of the parabola, and it is traced in the direction of the arrow here, because x is decreasing from infinity to 0, and so is y. So even though we got the same path, the manner in which it is traced is opposite to that of the last two examples. Okay, so one thing you want to notice or observe here is that we had in all three examples, in example 1, example 2, in all three examples we had the same path, but that same path, I gave you 3 different parametrizations for that. And in fact, there are infinitely many different parametrizations for the same path. Again, that should make sense to you, because we may have the same racetrack, but different race cars on that track will have different position vectors. Okay, so with that, let me stop with this introduction to vector functions and parametrized curves, and we will be looking at another example in the next video.